Are rapidly accreting black holes. So you have a supermassive black hole, and the matter doesn't just fall directly in. It has angular momentum, and it organizes itself into a disk. And the disk gets very hot and very bright, and the disk plus the black hole is the quasar. It's actually the accretion disk that we see as the source of all the light luminosity. The luminosity, the energy per second emitted, is equivalent to 10 to the 12, 10 to the 15 times the energy output of the sun, the luminosity of the sun. So it's equivalent to roughly that many stars. The size of the accretion disk where most of the light comes out in the ultraviolet continuum, is tiny. So a tiny fraction of a parsec compared to, these things sit in the centers of galaxies, and compared to galaxies which are tens of thousands of parsecs across. The source of the energy is gravitational energy released from the accretion, and that's just a mass accretion rate. Converting that to energy times some efficiency, which is about 10%, which is extremely efficient. 10% of the rest mass energy goes into light. The mass accretion rates are like a solar mass to something like 50 or 60 solar masses per year falling into the black hole. The black hole masses are something like 10 to the 8 up to 10 to the 10 times the mass of the sun. So quasars are doing this for a very short amount of time. Eventually you just run out of fuel. You run out of fuel and the quasar will turn off. And so the lifetime of a quasar is only something like 10 to the 7 to 10 to the 8 years compared to lifetimes of the galaxies they live in, which is billions. So they mark an active phase, an active accretion phase where the galaxy itself is also very active. I'm going to be talking about different components of this environment, and the most important one, besides the accretion disk itself, which is the source of the luminosity, there are outflows. It turns out that not all of the material accreting goes into the black hole. In fact, a good fraction of it, maybe half of it, that initially is beginning its way towards the black hole gets ejected. And there are powerful outflows. And they can be driven by radiation pressure, just the force of light pushing on matter. But also there can be, and there probably are, magnetic fields threaded through the disk, which as the matter is accreting, they will pull the magnetic field in with them. And then you put this whole thing in rotation, and charged particles want to follow magnetic field lines, and you can get matter flung out like beads on a string. I'm not going to talk too much about the physics of the flows. It's going to be more of this is going to be more of an observational talk, trying to measure basic properties. But let me put this also into the bigger context. When quasars were discovered in the 60s, they were interesting exotic objects and people studied them for that reason, and that's still true. But what's happened in the last 2 decades is that there's a much greater emphasis on trying to understand what quasars have to do with galaxy evolution. And part of that came with the discovery that present-day massive galaxies, including our Milky Way, have these supermassive black holes in them. They're mostly quiet. They're mostly not accreting or accreting at very low levels. But it meant that these supermassive black holes are natural byproducts of galaxy formation. So you make a galaxy, you make one of these black holes in the center. The epoch of quasars, which is what's shown in these plots, was billions of years ago. This is just number density of quasars versus redshift. So this is going that way is looking towards the past. And this is the present. In the present, there are basically no quasars. But the heyday of quasars was back at redshifts 2 and 3. So that's several billion years ago, kind of like 10 billion years ago. That's also the time at which massive galaxies were also most active, making stars, coming together, acquiring mass. That was a very active time in the evolution of the universe. And so quasars and galaxies were both doing their thing, mostly at these redshifts 2 and 3. a paradigm for how that might work, how quasars fit into galaxy evolution is shown in this sequence of plots, which is from this paper, Phil Hopkins. The idea is that early on, galaxies had less stars than they have now, so more gas-rich, and the universe was overall just more dense, and there were more mergers. So gas-rich galaxies can merge, and that merger causes compression and can make a lot of stars. The mergers can also disrupt orbits in the galaxies, and that's what can facilitate accretion down towards the very center to make the black hole. So the idea is you have a merger of gas-rich galaxies that triggers a huge burst of star formation. When stars form, you get supernova going off, the massive stars make metals, the metals get ejected into interstellar space, and those metals can form dust. They do form dust. And dust is like grains of sand, and it obscures things behind it. So these huge starbursts are also very dusty. And inside the starburst, the black hole is growing, but it's obscured by dust. Eventually, though, there's enough pressure that builds up from supernova going off and from the growing black hole with its outflows, we think, maybe, that's what I'm going to talk about, that there's a blowout in the galaxy and you expel a lot of the interstellar gas and dust, and eventually then you get an optically revealed quasar at the center, and then the quasar runs out of fuel, and then you just have a galaxy that's fading away with the dormant black hole inside of it. So my talk is going to be how we're trying to understand if this scheme is correct. And the basic question is, do quasars regulate galaxy evolution? And I'm going to divide this into two parts. One is to talk about quasar outflows way down at the accretion disk level, and then efforts to find quasars that are in this transition phase, where they're not completely buried in the dusty starburst and not completely revealed over here. They're still partially obscured by dust. That makes them red, like sunsets are red. So if you can find red quasars, they might be in this particular very active phase that's still young, and it's a way of sort of testing this scheme. So one of the basic questions about quasar outflows is, do they provide enough kinetic energy to have an effect on the host galaxies? Can they provide feedback to the galaxies and do things like expel the interstellar gas and dust or stir it up enough to disrupt star formation and kind of halt the evolution of the galaxy? Excuse me. So quasar feedback might be important if the kinetic energy luminosity, the kinetic energy per second, is greater than about 5% of the bolometric. And that's the amount that's been estimated. If you can couple that kinetic energy to the interstellar gas, that would be sufficient to blow out all of the interstellar gas, and that's going to shut down everything, star formation and further growth of the galaxy. But it turns out that you don't really need to blow everything out. If you just have an outflow that can shred interstellar clouds and in that way disrupt star formation, the threshold is lower. Just kinetic energy in these outflows of only 0.5% of the bolometric light energy output. And so can quasar outflows do this? Well, you can do a very quick back of the envelope calculation to show that they can if they have sufficient mass loss rates. Excuse me. It might be easier just to point. So the kinetic energy luminosity is just the mass loss rate and then 1/2 mv squared. We can measure velocities of the flows. If we take the velocity to be 1/10 the speed of light, we can compare this then to the bolometric luminosity. And that's just the accretion rate into the black hole times c squared and this efficiency factor, which is like 10%. I think that is a bad idea. So just adopting nominal numbers, V over C, and this is 0.1 C, you get that the kinetic energy luminosity for a mass loss rate equal to the accretion rate gives you 5%. So if we have mass loss rates that are just 10% of the accretion rate, we get above this threshold. So we're trying to understand if quasar outflows actually have those kinetic energies, and this is kind of the threshold for whether or not they can be important for galaxy evolution. So before I show you that, I want to show some pretty pictures of where we get data. Just to remind people that we've been getting data at the UC Keck observatories, which is incredibly important to us, and a lot of the reason we're here. But we're also getting data from surveys. The Sloan Digital Sky Survey has sort of transformed extragalactic astronomy. This is an infrared survey I'll talk about later. We're getting data at other telescopes. This is really a European telescope down in Chile. A very large telescope. Now they're making extremely large telescopes. Okay, so another picture of quasar outflows. I want you to kind of keep this in your head because I'm going to start showing you data, and it's easy to get lost in data. Here's the black hole again at the center. You're looking at the accretion disk edge on. There's an emission line region. This is stuff just above and below the disk. And then from that, roughly that location, there's an outflow. And observationally, one thing that's interesting to us is that if you're looking through this outflow, you're going to see the outflow in absorption. There are going to be features in the spectrum, absorption lines, due to gas in this outflow. But if you're not looking through the wind, you're not going to see the outflow. Or you're not going to see it in the absorption. And that's the primary way we measure these outflows is through absorption lines in the spectra. So here are some examples. These are rest frame ultraviolet spectra. So that's 120 nanometers. This is carbon-4 in emission. That's the broad emission lines. They're broad because it's a very dynamic environment and it's just Doppler broadened. But also then there's carbon-4, the gas in the outflow that's moving towards us, and it produces a broad blue-shifted absorption line. We call these BALs, broad absorption lines. They're a signature of these powerful outflows and a way to measure their energetics. And they can reach speeds of 1/10 of the speed of light or higher. But there are many other features in quasar spectra, absorption features, including these narrow absorption lines. This set right here happens to be also forming in a quasar outflow. If you're curious, I can tell you why I know that's true, but I'm not going to, it'll take a little while. There are also many other lines in these spectra, and we don't necessarily know just from looking at this if those lines form in an outflow or something else. I mean, for example, when we measure the light from a quasar, that light is traveling through everything that's between us and the quasar. So if there are intervening galaxies or just clouds of gas, they will also produce absorption at lower redshifts than the quasar. And so there's a mixture. And these narrow absorption lines can be sort of confusing. They can be in quasar outflows. If they're low speeds, they can be in the quasar's host galaxy driven by stars. Quasars can drive them to much higher speeds, but then they can also be just cosmologically intervening in other things. For the basic goal of trying to measure energetics, we want to measure the mass in the flow and the column density, just how much material is along the line of sight. If you're looking through the flow, how much material is along the line of sight, and then how fast is it moving? So this is for a particular, these are numbers for this particular outflow feature from a paper I wrote some years ago, just to kind of illustrate the point. Imagine just very crudely the flow is spherically symmetric, just a shell with some thickness and column density at some radius. So if it's spherically symmetric, then you multiply by 4 pi r squared, and the column density, you get the mass in the flow. But it's not really spherically symmetric. It's some kind of a conical thing. And so it doesn't fill, it fills some fraction of 4 pi steradians, like 10% nominally, just as a rough guess. So we get the mass in the outflow that way. We measure the velocities trivially from the spectrum. We get kinetic energies. This kinetic energy in this wimpy little set of lines here is small. That's equivalent to about 20 supernovae going off in the galaxy, which is not going to disrupt the galaxy or do a major thing. So this flow is not important for feedback. The point of this slide, though, really is that we want to get, well, the radius, I'm not really going to talk about. I'm going to talk about mostly this quantity. And velocities are easy to measure. The point I want to make is that these broad absorption lines appear to have much larger column densities by factors of 100 to 1,000. And if these broad absorption line outflows are present in all quasars, and it just happens to be that sometimes we're looking through them, most of the time we're not, but if the outflows are there in all quasars, then there are these powerful outflows present in all quasars, and we're trying to understand the energetics. Let me just show you a little bit about this. I have to show you some of the problems. You would think that measuring the amount of the material along the line of sight producing the absorption lines would just easily tell you how much material there is. The strength of the line correlates with the column density. The problem is that the flows literally do look like this. And so a feature like this that is not black, it's not saturated, can still have a huge column of material, but some of the light, if this is a generic light source and here's the observer, we're looking through this outflow material, and there are some lines of sight that don't pass through outflow gas. So this stuff just fills in the bottoms of the troughs, even though there might be enormous columns of material in the trough. So just looking at the features in the spectrum and measuring them has actually misled us for a long time, and it's kind of held the whole field back for a long time. But we've developed a technique to look at rare, low abundance, rare elements, low abundance elements, to see if they are also present in the spectrum. Things like phosphorus. Phosphorus is roughly 1,000 times less abundant than carbon. If phosphorus is present at all, it means there's enormous amounts of carbon, there's enormous amounts of everything else. There has to be an enormous column to get absorption in this very low abundance phosphorus feature. So we've started a couple different schemes to look for phosphorus and measure that to get true column densities and kinetic energies. So here's just a little bit more data. We use data from the Sloan Digital Sky Survey and the latest incarnation of that called BOSS, which is perfect for this study because it has better blue sensitivity, and we're looking for features that are rest-frame ultraviolet, redshifted, but we want to look at quasars in that epoch of activity 2 to 3. So we still have to look fairly blue to find these features shifted into the wavelength covered by these surveys. But these surveys were really well suited for this. And we found, so we require redshifts greater than 2.3 to get these features, that's this, phosphorus, shifted into the part of the spectrum measured by these telescopes. And the first thing we did was just look through a bunch of individual spectra to see what we found. And that became a paper, and that became many plots like this. These are the cases where it's extreme. We see the phosphorus is very strong. And it's common. But there are problems with measuring features out at these wavelengths beyond what I just mentioned. And one of them, I don't have really a slide to describe this, but I'll say it anyway. Shortwave of Lyman alpha, this is Lyman alpha, it's hard to read, in the spectrum of the quasar. Shortwave of that in the spectrum is going to be Lyman alpha in intervening material. Intervening galaxies and clouds have hydrogen in them, so they will produce Lyman alpha absorption at all of these different lower redshifts than the quasar redshift. And so there's a huge amount of contamination. And the cases I'm showing here are where just accidentally the contamination along our line of sight is not that bad. but in most cases it's bad. A way to get around it is that the intervening material is just sort of randomly spaced in redshift and in wavelength that we measure. And so if you average a bunch of spectra, you get a suppression of the flux, a sort of average suppression of the flux, but the features go away. So if we take median spectra of many quasars and shift them to the absorber frame, that is the frame of the BAL absorber, we get things like this plot here. And you can think of these three panels as just grouping quasars by the strength of their broad absorption lines. So the middle one is sort of typical. These are strong broad absorption lines, and these are much weaker, we call mini-BALs. The point is, they all have phosphorus 5. In a median spectrum, they all have phosphorus 5, so phosphorus 5 absorption is typically significantly present. Something else is that you can see in these spectra, because they're shifted to the absorber frame, and we have good signal to noise, is that these doublet ratios are 1-to-1. If the gas was, I hesitate to use this word, but if the gas was optically thin, that is not very, if the mean free path of a photon is less than 1 through the medium, you're just seeing through the whole thing. And you would get 2-to-1 ratios in these doublets. That really needs more explanation, just take my word for it. But if it's saturated, they become 1-to-1. Saturated means there's a lot of phosphorus 5, there's a lot of silicon 4, much more than is indicated by the small depth of this line. So these are little clouds partially covering a big emission source, but little clouds with a lot of column density. So phosphorus 5 is not only present, but it's saturated. So we get lower limits, and it turns out to be very large lower limits on the total hydrogen column density. So let's just look at some of these numbers. It takes photoionization models. The gas is heated and ionized by the light from the quasar, so photoionization. And we run simulations like that to get the ionization state of the gas and convert line strengths into column densities and things like that, and I'm skipping all those steps. But we know that phosphorus 5, the degree of ionization in phosphorus 5 is very similar to carbon 4. They should coexist in basically the same gas. If there's a range of ionizations, these two ions are going to be co-spatial. But phosphorus is much less abundant. So this should not be present, a phosphorus 5 broad absorption line, unless these guys are very saturated, carbon 4, oxygen 6. The lines of the more abundant elements, the more abundant ions, are extremely saturated. And the column densities are huge. This, again, this optical depth is just a measure of the amount of saturation. 1 is intermediate, 30 and 1,000 is huge. The column densities, these numbers won't mean anything to you, but they're 100 to 1,000 times bigger than the numbers I gave you before. So large column densities and broad absorption line outflows, and much larger than we would have deduced just from looking at the lines of these more abundant elements. Plugging numbers into those equations to get kinetic energies, pick a sort of typical radius, 3 parsecs from the black hole, the radius of where the outflow is. A typical speed, a typical global fraction of 4 pi, 10%. You get a mass loss rate of about 12 solar masses per year, similar to the accretion rates. Kinetic energy, luminosity, that turns out to be typically around 2% of the bolometric luminosities. So what we're claiming is that quasars typically have these large kinetic energy luminosities, which are sufficient to drive feedback in the host galaxies. Now, whether they actually provide feedback to the host galaxies is really another question, because it depends on the outflow coupling to the gas. But the quasars are providing sufficient energy, apparently, to do that. Okay, so that's all I'm going to say about the outflows specifically. Back to this chronology. So there's a merger, a massive starburst inside of here. You have a dusty starburst inside of here. The black hole is growing, but we can't see it visibly. It's obscured. It gets revealed when there's a blowout and the gas and dust gets expelled, and then you get a normal blue quasar at the end. But in the middle here, these sort of transition objects, we're looking for those. Quasars that are in the transition phase, maybe participating, maybe driving the blowout. So signatures of young quasars in this phase would be definitely things like red colors, very obscured to not obscured. Excuse me, something intermediate. Red colors, partially obscured. They might, since this is a very active phase and you're dumping a lot of material in towards the center, potentially they could have higher accretion rates, more powerful outflows, more common outflows from the accretion disk, higher star formation rates associated with this younger phase in the starburst over here, and other things I'll mention later. So red quasars are another thing that we're focusing on. We identify red quasars by combining data from two surveys. Again, the Sloan Digital Sky Survey, which measures, finds things in at visible wavelengths, our observer frame visible wavelengths. Data release 12 for the astronomers, that's the most recent big release. About 300,000 quasars in the survey across visible and even the near-infrared wavelengths. We combine that with this satellite called WISE, which measured the sky in the mid-infrared from 3 microns to 22 microns. And in the first part of this, I'm just going to talk about some particular filters, combinations. We've been studying red quasars in 2 different ways, so this is kind of part 1 of that. Part 1 of that is using the data I just mentioned. Let me actually clarify this a little bit more. The Sloan Digital Sky Survey is what finds the quasars. They take pictures of the sky, they measure the colors of things in the visible, they identify things that kind of look like quasars in their colors, then they get a spectrum and confirm it's a quasar. One of the things that the most recent version of this survey did to find more quasars at higher redshifts, I didn't explain this figure, but this latest data release found a lot of quasars at these redshifts, the interesting redshifts. To do that, they had to select objects from the images that are redder, and that means more contamination by stars and galaxies, which are also redder. It turned out they took spectra of things that they were hoping were quasars, and only about half of them were quasars, and the rest they just had to throw away. But it's really good for us because they're looking for redder things. They went fainter, deeper in the survey, and it's good for a red quasar study. So Sloan finds the quasars, and then these just provide an additional near-infrared color. So what we did is select quasars from the Sloan catalog in a certain redshift range, and using certain filters. These are Sloan filters. That's one of the WISE near-infrared, mid-infrared filters, to sample 0.2 to 1 micron in the quasar rest frame. And that's to look for reddening across the part of the spectrum that is the thermally emitting accretion disk, the hot, flat accretion disk. And light at different wavelengths in quasars can come from different things, and this avoids that. And avoids starlight contamination from the surrounding galaxies, et cetera. So with a sample of almost 100,000 quasars, is Bob here? Bob's here. Bob loves these kind of dotty plots, so there's going to be some of these now. This is the color. This is I. This corresponds to like 0.2 microns in the rest frame, and W1 is 1 micron in the rest frame. Going up is red. That's all you need to know. And I magnitude going this way is fainter. And so these quasars here have kind of normal blue colors, and then as we go fainter, we find more and more red ones. This is just an illustration of where the filters lie on a typical quasar spectrum. We're using this filter and filters over here. 1 micron and something like 0.2 microns. We have a quantity called EB minus V, which is basically just combining several colors into a measure of the amount of reddening. We define zero reddening relative to bright quasars. We assume that the bright ones are not very obscured. So these guys kind of define a baseline for what is a non-reddened color. These guys are red. There's a distribution about zero reddening, and that has to do with you're combining data from 2 surveys and taken at 2 different times, and quasars can vary. And even if they don't change color, if you take an image in one filter at one time and then the other filter at another time, you're going to get scatter in your colors. There's also just, quasars are not stars. They're not as simple as stars. They're not as homogeneous as stars. There's variations quasar to quasar in just what they look like, including just the intrinsic emitted spectrum. So there's going to be some distribution about zero that is just normal scatter. But beyond that, there's this red tail that are quasars reddened by dust. So we can count how many of these red quasars there are. And here's just another histogram plot of, excuse me, the number, and then in parentheses, the percentage of quasars at this EB minus V that are reddened by dust. So we found a total of almost 46,000 red quasars. These levels of reddening won't mean anything to you, but this number, 0.3, corresponds to 10 times suppression in the near ultraviolet, 10 times suppression of the flux, the light emitted, the light observed. We found many more red quasars in previous studies that did targeted work and didn't use such a big survey. That's just something for the astronomers who you can ask me about that later. What I want to talk about is the properties of these quasars. So I'm just condensing this big study into a couple things to talk about outflows related to redness. We examined a full range of quasar properties correlated with reddening. That was the goal. But what I'm going to talk about here is outflows correlated with reddening. So we can do something very simple, like just count the number of absorption lines in different velocity ranges. So this is narrow absorption lines in carbon-4, near the quasar redshift, and then including some a little bit farther from the quasar redshift. So these are probably outflow lines. Most of them are going to be outflow lines, but some of them might be some ambient material, other stuff. The point is that as a function of reddening across this distribution, the fraction that have these narrow absorption lines is much higher as you get redder and redder. So red quasars have a lot more narrow absorption lines, probably outflow lines, narrow outflow lines. The more direct signatures, the more confident signatures of outflows are these broad absorption lines. So in the survey, they identify broad absorption lines by visual inspection, VI. It's the simplest way to do it. You trust your eye more than a lot of automated schemes to measure things. And again, the fraction of quasars that has a broad absorption line outflow in its spectrum goes way up. So this is a percentage, goes way up as you get redder and down as you go blue. That's for these broad absorption lines. There are things that are not quite as broad as this, and we measure them in different ways, but it includes mini BALs. And when we combine BALs and these sort of narrower features called mini BALs, we get the same result. Any kind of broad outflow line, the incidence of that goes way up in red quasars compared to blue quasars. So outflows are much more common in red quasars. Something else, almost as an aside, but if we look at other lines, a line with lower ionization. These lower ionization lines require larger column densities. You can show that they're correlated with larger column densities. And it's because if you've got an ionizing spectral source over here and a thick slab of outflow gas, the front of that slab of outflow gas is going to be very highly ionized because it's exposed to this radiation field. But at the back of that, you get radiative shielding, bound-free absorption in the gas, can shield the back end of it, and you get lower degrees of ionization at the back end of a large column. And that's all just to say that these lower ionization lines also increase dramatically, even more dramatically, 30 times more in red quasars. And it's a signature not only of more frequent outflows, but larger column density outflows, more massive outflows, more powerful outflows in redder quasars. Okay, back to this picture just to remind you. The completely obscured phase with the starburst, the black hole is growing in there. We have a transition phase, blue quasars. We're still interested in red quasars, but now we want to look at the most extreme ones. The previous survey was looking at quasar properties as a function of reddening in a big sample of almost 100,000 quasars. Now we want to pull out the most extreme red quasars to see if those should be the youngest in this evolution scheme, the most buried, with possibly the most exotic properties. So we looked for what we called extremely red quasars using these same surveys. Now we're using a different color combination. W3 measures things out at 3.5 microns roughly in the rest frame. And so instead of measuring the color across the rest frame UV invisible, which is sensitive to dust properties and the geometry, we're now looking at something farther out in the mid-infrared compared to the UV, so it's more sensitive to the overall UV suppression and less sensitive to the details of how reddening works. So it's valuable for finding the most extreme, obscured objects independent of how the dust properties work in the geometry. So we defined ERQs by having extremely red colors in this rest frame UV, that's 0.2 microns, and this W3, which is about 3.5 at the redshifts of our survey, which I didn't write down, but it's also about 2.5. That's where most of the objects are. This is a median spectral energy distribution of the extremely red quasars. All these are normalized at 4 microns. And then they get, so this is the ultraviolet here. These green and blue lines are just normal, unobscured quasar. This is what most quasars look like. And these guys are suppressed a lot in the ultraviolet. They're enormously luminous, several times 10 to the 14 times the luminosity of the sun. They have to be luminous or we wouldn't find them in the survey. They're extremely red, and that means they're suppressed in the ultraviolet, but we find them in the Sloan Digital Sky Survey, and to be in the survey and to be very suppressed in the UV, they have to be luminous. So we can only find very luminous objects this way. To find fainter, less luminous red objects, we need a much deeper survey. Yeah. Yeah, there's all kinds of selection biases against finding these things. We've definitely just found the tip of the iceberg. Yeah, you know, I had a whole thing here about hot dogs, and I took it out because it's just. So hot dogs are. Okay, so a little bit of history to how this worked. DOG means dust obscured galaxy. That's an old term that's like 10 years old. People were looking for galaxies, dust obscured galaxies, in that evolution, that starburst evolution phase, doing the same kind of techniques, but they were just interested in galaxies. So they found DOGs, dust obscured galaxies. Then people did a little bit more with WISE, and they noticed that they have very hot colors in the mid-infrared. So you have dust-obscured galaxies, but they're actually powered by an obscured quasar. There's very hot dust across the mid-infrared. This is dust near the black hole, near the accretion disk. So they're hot dogs. So it's another, these are each of these other curves, there are other teams looking for red quasars. We've done it in a particular way, they've done something else. Ours are, I didn't want to go into that, but ours are better. I could explain that more maybe at the end. Well, I mean, to understand why they're more interesting is that they have this completely unique set of exotic properties. We select them just based on color. That was the only thing, just based on this color. And by the way, they have space densities, they have large luminosity, space densities of a few percent of blue quasars if you match them in luminosity and redshift. These are a few percent of that. That's consistent with the fact that we're missing many ERQs, that they're just a tiny fraction of the blue quasars, but it's also consistent with the red phase being shorter lived than the blue phase of quasar evolution. Most of them will be in that older bluer phase, and the red phase, where they're just becoming unveiled in that blowout, could be very short. And so you don't expect to find a lot of them in that short evolution phase. And so the numbers we find are consistent with the evolution scheme and the fact that we're not finding all of them. But the real interesting thing about extremely red quasars is they have exotic spectral properties. Now this won't mean too much to you. Here's just how we define them. That's the redshift range, large luminosities. These are again rest frame ultraviolet spectra. And I think maybe this shows better how exotic they are, because this purple line is a composite median quasar spectrum put together for quasars at sort of lower redshifts, redshift 1, but it's a typical quasar spectrum. And all I did here is normalize it so they match in the continuum. And you can see the lines in the typical quasar spectrum are way different, way weaker than these ERQs. So this is rest frame ultraviolet. I'll talk about these lines more later. Well, yeah, I'll just mention that. I'll say that more later. But exotic spectral properties. We can show that they have systematically exotic properties by plotting some of these properties. They have strong lines. This is rest equivalent width. It's just the strength of the line relative to the continuum. The strength of the line relative to this continuum. It's huge for these guys. Large equivalent widths, and this is a measure of the shape of the line profile. And you can think of this as, these are sort of like the Empire State Building, straight up and down. And these are like the pyramids in Gaza. Okay, so they're like this. Quasars have a wide range. The ERQs are up here with a certain kind of profile and very strong. Exotic line ratios that combined with these strengths separate them from the quasar population. They also have, not shown here, are signatures of outflows. A high incidence of broad absorption line outflows in their spectra. A high incidence, I think, we're still working on this, of at least very large broad emission line blue shifts. So let me just say a little bit about that. These are the emission lines, and I mentioned, like here you can see an absorption line. That's the material flowing towards you, blue shifted outflows. But even the emission gas above the accretion disk, if the disk is like the plane of this board, and you've got stuff flowing towards you, that emission is going to be blue shifted. The red shifted emission on the other side of the accretion disk is obscured by the disk. So we would see a net blue shift if the emission line region is flowing out as well. And that seems to be a common property, these blue shifted emission lines. and then blue shifted O3, which I'll mention a bit later. But it appears all these things together identify ERQs as a unique population that might be a young quasar population, definitely though with exotic properties and some kind of exotic physical conditions that involve outflows. Just a little bit more evidence for the outflows. So this list, basically. BALs and mini-BALs. The spectra are, it's hard to see the BALs because the lines are so strong and the spectra are kind of crappy, but they're common. When you zoom in and look closely, these kind of features are much more common in ERQs than other normal quasars in the survey, normal blue quasars, like other red quasar samples, like I mentioned earlier in other studies. The blue shifted broad emission lines, another signature of outflow way down at the accretion disk level, that also seems to be common. Just as a little aside, it's very hard to measure these outflow speeds accurately because when lots of things are shifted, we don't know what is the actual redshift of the black hole sitting there at the center. What is the systemic redshift of the system? We're measuring features in gas that's moving. But we can do that in some of these spectra, looking at this narrow Lyman alpha emission line, which I think it's narrow, so it's not down near the black hole. It's not in a dynamic environment that would make the line broad. So it's something farther out. It's probably emission farther out in the galaxy, maybe way out in the galaxy, and altogether it's kind of then giving us a measure of the systemic redshift of the galaxy. If we use that to define the redshift, in these cases where that narrow spike is present, so this is that Lyman alpha spike, then this is the predicted position of nitrogen 5, this is the predicted position of carbon 4, and the redshift of this spike, and you can see the broad emission lines are blue shifted a lot relative to that systemic by these many kilometers per second. So those are big shifts. Those are anomalously big shifts, and this one's ridiculous. But I think it's right, and it seems to be common. I haven't seen this in any other quasar spectra. Here's just an exotic case. It's a broad absorption line quasar where now I've defined the redshift by low ionization lines, which we think should be sitting, it's closer to the accretion disk. They're narrower. They should be situated closer to the accretion disk and not part of the flow. When the gas starts flowing, it gets more diffuse, and the ionization level goes up. When the densities go down with photoionization, the ionization goes up. So the higher ions are the ones that are participating in the flow, and the lower ions should be a better measure of the systemic redshift. If we use these narrow, low ionization lines to define a redshift, we see huge outflows in the broad absorption lines and the broad emission lines in this one case. Okay, so now the last thing then is, this is a study of the forbidden oxygen 3 lines that's being led by Serena Perrotta, where she went out and got near-infrared spectra of 28 of these ERQs to see if the extreme velocities and blue shifts we measure in this feature are common. There was a paper published a couple years ago that included these data. And a couple things about that. Again, this purple line is a typical quasar spectrum. These lines, forbidden oxygen 3, those features are typically narrow because they require low densities. It's a forbidden line. The excited state would get collisionally de-excited if the gas is dense. So it requires a low density, not near the quasar, but someplace further out in the galaxy, usually. So the lines are narrow, and there's a pair of them, and they're easily resolved. But in the ERQs, there can be enormous monster messes, broad and blue shifted. up to 6,000 kilometers per second. Because they're forbidden lines, just based on that and photoionization, we think they should be not identifying outflows right directly from the accretion disk, but identifying outflows that are on a much larger scale, hundreds of parsecs at least, kiloparsec scales probably. And so part of Serina's study was to measure all these things and then compare to blue quasars, and I'm just going to show you a few things. And she can interrupt me if I get it wrong. So this is just examples of all the work that went into it. These are the pair of forbidden oxygen 3 lines. Right next to it is H beta, hydrogen H beta. And there's deblending that needs to be done, multiple components. The idea is to fit the lines and measure basic quantities. And I'm just going to show you real quick a couple of the results. When we measure the outflow speeds, the speed in the blue shifted wing of the oxygen 3 profiles, which we think is a good measure of the outflow speed. That's called V98 in these plots, this plot. And then here we have a measure of the luminosity. Because they're suppressed in the ultraviolet and the visible, we can't really just integrate over all the light from the quasar to get we can't use that to measure the luminosity. We have to go out in the infrared where the obscuration by dusk is sort of negligible. So this is like a surrogate for the bolometric luminosity of the quasar. So luminosity here and outflow velocity here. And these are blue quasars from 2 different studies in the literature, mostly this Shen study. And they find a very weak trend. They discuss that these outflow velocities in oxygen 3 flows seem to increase slightly with luminosity. And that makes more sense. You've got a more luminous quasar, you've got more radiation that can push stuff. But what Serina found with the ERQs is that they are characteristically have much higher speeds, and it's not a luminosity factor. It's related to the red color. So here's our color I-3, and the threshold for ERQs is here roughly and up. So these are all ERQ colors, much higher speeds. So related to red color, but not luminosity. So the picture of ERQs is that they appear to have outflows on basically all scales. We find a higher incidence of BALs and mini-BALs. We find these blue shifted broad emission lines. What's illustrated here is, again, you've got the black hole in the center, the accretion disk. This is the part emitting the ultraviolet continuum. Broad emission line clouds above and below that, and outflow above and below that. There's probably a dusty outflow. The whole thing seems to be just extremely outflowing, more than other quasars. In fact, I'll just mention the broad emission line, if it's part of an outflow, it becomes more extended. When it becomes more extended, it intercepts more of the quasar light and reprocesses that into a stronger emission line. So the strong emission lines we see in these objects can also be related to the fact that this is outflowing and more extended. So it all kinds of fits, it all sort of fits this picture of these being extreme outflow objects, strongly correlated with extremely red colors. Another plot from Serina's paper, which is in the works, is how much kinetic energy is in these flows. So I'm skipping a lot of the details. And just plotting estimates of the kinetic energy per second in the flows, these oxygen 3 flows, again versus a measure of the bolometric luminosity. And these are all the blue quasars from these other 2 studies. This is as a fraction of the bolometric luminosity. So 0.1%, 1%, 10% of bolometric. It's in this range that you want them to be important for feedback to galaxy evolution. And our best estimates are that the ERQs are characteristically all in that range, whereas blue quasars maybe not. At least blue quasars as measured in the O3 outflows. There's lots of others. We had to make assumptions about physical properties, and you can ask me about that if you like. But it's consistent with this idea that they're extremely powerful outflow objects. There are efforts underway now, so we know that the O3 outflows have a lot of energy. We think, because it's a forbidden line and low densities, we think these outflows they're not down near the accretion disks, they're more extended in the galaxies. But are they actually affecting galaxy evolution? Are they providing feedback to disrupt star formation or cause a blowout? One way to address that is to look to see if these flows with this energy in oxygen 3 are actually spatially extended. And so we're getting data now with OSIRIS on Keck to try to spatially resolve these outflows. I can say more about that, but we're hopefully getting more. Another way to do it is to see if directly there are outflows affecting the host galaxies of ERQs by looking at the molecular gas emission. Star-forming environments have to be cold. So the star formation around quasars in any kind of star-forming environment is cold and it contains molecules. If ERQs are disrupting star formation and really providing feedback, they would be disrupting these locations of star formation. They would be stirring up the molecular gas. They would be driving out the molecular gas further out in the galaxies. So we're getting data at a sub-millimeter wavelengths using something called the ALMA array in the Atacama Desert, which is sort of the foothills of the Andes in Chile. And I'm only going to show you one plot of that because we're getting, actually the data the survey's just been finished, but we haven't looked at it yet. But I can show you a little bit. We measured 15 ERQs, and our goal is to find if ERQs are different than other quasars at the same redshift, same luminosities. Are there interstellar clouds, the star-forming regions, more disturbed than what a normal quasar would do, a normal blue quasar? Are ERQs special in some way? So to determine if they're special or different than other quasars, we need control samples. So we've also getting control samples. But this is just data for one ERQ in the continuum. At these long wavelengths, we're measuring the thermal emission from dust farther out in the galaxy. And you can crudely from that, it's star formation that heats this dust. Hot stars illuminate the dust reprocesses that and glows in the sub-millimeter. From the dust luminosity, we can guess the star formation rates, a few hundred. We also measured molecules, CO and carbon-1, which is something else, another emission line that happens in this very cold molecular gas. And this part of the experiment, initially, we didn't do so well because the antenna at ALMA you can only tune to a narrow range of frequencies. And that means you got to know where the redshift is. You have to know where these lines are going to be. And these lines are so shifted that they were off the edge of the band. We got the edge of some line, but we don't really know what it looks like and how extreme the outflows are. But the shifts are huge from where we thought they should be. So this actually turned up in the band setting of what we thought should be another line, a CO line, and we got this line in the wrong setting. So hopefully in the new data we did it better. But the point is these lines are very strong. They seem to be broad, shifted, and there's even evidence for an extension, which hopefully we can tell if that's been ejected or not. And with the control samples, make comparisons of these kind of image and the kinematics in this gas to more quiescent quasars. Okay, so just a real quick summary. Accretion disk outflows, the first part of the talk, the phosphorus 5 stuff, we think that quasars typically are putting out enough kinetic energy to be important for feedback to galaxy evolution. Then when you look at red quasars, we find that all varieties of outflow absorption lines are more common and stronger in red quasars versus blue quasars, consistent with more common and more powerful outflows occurring in this possibly young, obscured evolution stage. Then when we look at the most extreme red quasars, they have more exclusively exotic properties, again tied to outflows. And the O3 emission is really spectacular, indicating some kind of more extended outflow and is the best candidate for driving feedback. And we're going to explore that more. So that's it. Yeah.
So we have a lot to talk about, of course. But just briefly, your ERQs, are you at the point where you can conclusively exclude the possibility of our orientation origin for all the properties?
Well, so that's a really good question. I think that the thing that excludes them is the O3. Because the O3 should be extended beyond the torus or something that could be like a typical, could hide something near the accretion disk. So there's really no way to hide that. If they were, if normal blue quasars had that kind of thing, we should have seen it. So I can't think of a reason why it would correlate with red colors unless it's something else. But it can't be, you can't hide it. If it's way out here, it's oriented like this or oriented like that, you're going to still see it. So I think that's what tells its orientation and not, and more likely to be actually some kind of evolutionary bigger thing tied to the galaxies. The ALMA results will also, because it's looking at the galaxies to see if the galaxies are different, that will make another direct connection to evolution rather than something, but we haven't gotten far enough with those data yet.
I had a question on that front. So what about the host of these extreme objects? Are they undergoing mergers or for some reason, what makes them special?
Yeah, so that's a really good question, and we got time on the Space Telescope. This is actually Nadia Zukomska led this. We got time in the Space Telescope to look at something like 15 or 20 ERQs, and redshift 2.5, looking at the host galaxies, it was just too hard. And it failed. But JWST is going to answer that question. But we don't have the answer yet. Well, I mean, the ALMA observations will do that because the ALMA observations are going to tell us if the molecular gas is churned up or outflowing or doing something odd, and that would be an indication. If that correlates with ERQs, if that's a unique ERQ property that their molecular gas is churned up, then it's probably driven by their outflows. Other people have done things where you can map where the O3 emission is coming from, and then beyond that you look for, there's like a bubble where the O3 is, and then beyond that there's something else going on. People have tried to estimate how much star formation there is in the O3 regions versus beyond that where the O3 hasn't hit. And there's evidence from that the O3 outflows can be driving or disrupting star formation. We don't have those kind of data yet. We might get that eventually when we do these OSIRIS observations on Keck, but the people normally do that kind of thing, but they ask that question sort of generally. You want to do it in a situation where it's easier, so you're looking at things that are lower redshift, and you find some good example where you can map things with good signal to noise. We found exotic objects at these high redshifts, and now to do that, it's going to be hard to get good maps and establish the relationships. But so what we're doing is just looking at correlations. This feature is common in ERQs, these outflows. If they have churned up interstellar gas, if they have these prominent, they do have these prominent O3 outflows. I mean, if it all fits together, we don't have to actually see it. We can just kind of connect the dots. Yeah, so actually there have been papers written about that, and the argument was that red quasars are a little bit more clustered, meaning they have more galaxy companions. But then that more recently went away. And so the signal for that was very weak. So if there is any kind of over density around these objects, I think it's small. We haven't looked at that. But in the literature, it seems pretty inconclusive.